We shall now move on to the next unit, kinetics of rigid bodies. When we have a rigid body of a definite size and mass that is acted upon by a number of forces, say F1, F2, etc. Now this assume that this corresponding system of forces is not concurrent. If they are concurrent, that means they are acting at the same point, or the line of action meets at a single point. In that case, the body will tend to have only translation. Okay, if the corresponding forces are concurrent, then the corresponding rigid body will have only translational motion. In case the corresponding forces are not concurrent, in that case what happens is that the rigid body will have both translation plus rotation. Translation as well as rotation. So in a general system of forces, if they are acting on a rigid body, then this force system may be replaced by a resultant force acting at a point and a couple. So as such, I can replace this corresponding system of forces here into a single resultant force that is acting at some point here and a moment. Okay, now this corresponding point can be any point. So as such, the replacement of a general system of external forces into an equivalent force coupled system, which you must have studied already in statics, the same thing we had done here. In a rigid body motion, the most commonly accepted point as such is the mass center. Okay, so here I will show you a system of forces here and the mass center G here. Okay, now the resultant of this force system can have a resultant value of sigma F and a corresponding moment or couple, okay, with respect to the point G or the mass center as shown in this figure. This corresponding equivalent system can be obtained when a general system of forces act on a rigid body. So here I have drawn the free body diagram, the equivalent force couple diagram and the kinetic diagram. Okay, kinetic diagram as such, the corresponding sigma F will be indicated by mass into acceleration. So as such, I can write here once again, a general motion involves both translation as well as rotation. Now, the corresponding translational aspect of the motion can be expressed by the equation sigma F equals m into a. Okay, this we had already discussed when we considered a system of particles. I told you earlier that a corresponding rigid body can be assumed to be a collection of a system of particles. Here m will be the total mass. So as such, sigma F equals m into a, where m represents the total mass of the rigid body and a represents the acceleration of the mass center. So this will be the acceleration of the mass center. Okay. Now the rotational aspect. The rotational aspect is governed by another equation which we had studied when we discussed angular momentum. We had said that sigma mg is equal to hg dot, where sigma mg is the corresponding moment acting at the mass center and hg is the angular momentum. Okay, this equation is called the moment of momentum equation, which we had studied earlier. The equation is referred to as moment of momentum equation. Okay, so it sigma mg is equal to the derivative of hg, or the derivative of the angular momentum. So as such, a general motion, okay, a general motion, since it involves both translation as well as rotation, the corresponding equations are sigma f equals ma and sigma mg equals hg dot. Now we shall now concentrate our corresponding study for finding hg, the angular momentum of a rigid body. Now we had already discussed this aspect when we considered a system of particles. Okay, a system of particles. I told you a rigid body can be considered to be a system of particles, and then we had derived the equation for hg. The same thing once again we'll try to do it, but in a slightly different way. Okay, now consider I have a rigid body, okay, with a general motion in space. Now here xyz, the capital xyz represents the corresponding inertial reference frame, okay, and this corresponding rigid body is undergoing an angular velocity omega at an instant of time. Okay, now we shall look into finding the corresponding angular momentum of this body with respect to three different points. One is the origin, the second is any arbitrary point, and the third is the mass center. We shall try to find the angular momentum with respect to these 3 points, and we shall see the relationships, the equations. Okay, so first I shall go after angular momentum with respect to origin O. Now O is the origin here. The corresponding angular momentum with respect to the origin of the inertial reference frame. The origin of the inertial reference frame is also called as absolute momentum. It's actually angular momentum, okay. Angular momentum. Now this corresponding equation we had already studied it when we considered a system of particles. So as such, the equation was HO equals sigma Ri cross Mi Vi, okay, or R and V are the corresponding vectors, okay. Now this corresponding rigid body here, I assume it to be a collection of particles. Let the corresponding mass of one particle be denoted by Mi, and the corresponding displacement with respect to the origin is given as Ri, okay. Now the linear velocity of this corresponding particle will be Mi Vi, okay, Mi Vi. So the angular momentum of that corresponding particle will be Ri cross Mi Vi, where Ri and Vi are vectors. So as such, if I take the sum of all the corresponding particles, I get the angular momentum of the rigid body. The rigid body. Now since it is with respect to O, I write here O. Okay, that is how you got this corresponding equation. We had already discussed this part earlier. Okay, so here remember one thing, Vi is the velocity of the particle Now this velocity is measured with respect to xyz. So with respect to the capital XYZ coordinate system, or I can say the reference, or I can say the primary inertial reference frame. Okay, so the thing is that I am viewing this body as a collection of infinite number of particles. Okay, so this all the angular moments of each of these particles can be added together to get the angular moment of the rigid body. This is one aspect how I do it. Okay, but instead of considering it as a system of particles having say a mass mi, I shall consider a differential element of mass. So instead of mi here, I shall consider a differential element of mass dm. Okay, in that case, angular momentum with respect to the point O, so HO, can be given as, instead of sigma I will write integral. Okay, so as such I am integrating the angular moment of these different elements having a corresponding differential mass dn. So HO equals R cross V into dm. Okay, this is how I write in case I consider it as a differential elements. So I converted sigma into the integration part and R cross V dm. So V dm as such represents the linear velocity. Cross product of R will give you the angular moment with respect to the point O. Okay, this I can also write it as R cross. Now you see this rigid body is undergoing an angular velocity omega, with respect to the reference frame xyz. So as such I can say that v is equal to omega vector cross r vector. Okay, so if I replace this here in this equation, so here r vector cross omega vector cross r vector into dm. Okay, so here r vector represents the position vector of the differential mass dm, and here v represents the velocity vector of the differential mass dm. Okay, now you see this corresponding part here is a triple product. Okay, it is actually a triple product. Now suppose the corresponding r vector I represent it as x into I cap plus y into j cap plus z into k cap. Okay, and the omega vector, okay, omega x into I cap plus omega y into j cap plus omega z into k cap. So if I substitute these corresponding values in this corresponding equation and I take the triple product, okay, r cross omega cross r, what I would get is HO equals I into y square plus z square into omega x minus xy into omega y minus xz into omega z dm plus j cap into minus yx into omega x plus z square plus x square into omega y minus yz into omega z multiplied by dm plus k cap into minus zx omega x minus zy omega y plus x square plus y square into omega z df. So this corresponding equation I will get. In case I replace the corresponding r vector as xi cap plus yj cap plus zk cap and omega as omega xi cap plus omega yj cap and omega z k cap. This is what happens. Okay. Now remember this corresponding equation. Okay. Now next we will go to finding the angular momentum with respect to the mass center. Okay. Angular momentum with respect to mass center. We shall look into that aspect. Now, what I do is that now you have the inertial frame here, capital XYZ, okay, and then you have the rigid body here. This corresponding rigid body is undergoing an angular velocity omega, okay, angular velocity omega with respect to the inertial reference frame capital XYZ. Okay, G is the mass center of the rigid body, and as such the velocity of the mass center here is shown here. The velocity of the mass center. Now what I do is that I attach the secondary reference frame small xyz with its origin at the mass center such that it is embedded within the rigid body. That means the corresponding xyz reference frame, the secondary reference frame xyz, also undergoes an angular velocity omega with respect to the primary or inertial reference frame capital XYZ, since it is embedded within the rigid body here. Now let this rigid body be considered as a system of particles, a system of particles. One of these particles is shown here mi, and the corresponding position vector of this particle I with respect to the secondary reference frame small xyz is given as rho I. So here the angular momentum of the rigid body with respect to mass center hg will be equal to sigma rho I cross mi vi. Okay, rho I cross mi vi, where rho I is the position vector with respect to small x y z. Okay, and vi is the velocity of the particle mi with respect to not small xyz but capital xyz. Okay, that you have to remember in mind. Okay, vi is the corresponding velocity with respect to not small xyz but capital xyz. So in that case I can express vi is equal to v bar plus omega cross rho I. Okay, this corresponding relation becomes valid. This we had already studied here. So here v bar is the velocity of the mass center, omega is the angular velocity of the secondary reference frame or the rigid body, and rho I is position vector of the rigid body. Okay, so substituting this corresponding equation in hg, I will get hg is equal to sigma rho I cross mi into v bar plus omega vector cross rho I vector. All these are vectors. In the earlier case also all these are vectors. Okay. I hope you can understand that. Now this I'll close it here. Okay, if I expand this corresponding equation, I would get sigma rho I cross mi v bar plus sigma rho I cross mi into omega vector cross rho I vector. If I expand this, I would get this corresponding equation. Now, since here v as such is the velocity of the mass center, it does not have any relationship with sigma here. So this equation I can change it into minus v vector cross sigma mi rho I. Okay, I will reverse this, so as such I'll get a negative sign here, and this sigma does not have any effect on this, so I'll transfer mi to this corresponding part. So minus v vector cross sigma mi rho I plus the remaining part remains as it is. Now this corresponding part here, mi is the mass of the ith particle and rho I is the corresponding position vector with respect to the mass center. So as such, sigma mi rho I will be equal to 0. So you can write the equation Hg is equal to sigma rho I vector cross mi into omega vector cross rho I vector, this one. Now instead of taking the corresponding rigid body as a system of particles, I consider differential elements dm, then the above equation can be written as Hg equals integral rho cross omega cross rho into dm, rho vector omega vector rho vector. So this is the corresponding angular momentum of the rigid body with respect to the mass center. Earlier we had seen the corresponding angular momentum with respect to the origin of inertial reference frame, HO equals integral r vector cross omega vector cross r vector into dm. So it's almost synonymous. Instead of r vector, it has become rho vector. Okay. So as such, we had find out the angular momentum with respect to the mass center G and with respect to the origin of the inertial frame O. Now next we shall concentrate on finding the angular momentum with respect to arbitrary point. Arbitrary point, say the arbitrary point is A. Okay. So the same principle gets followed here. I'll write it down very fast. HA equals sigma rho A cross mi vi. These two are vectors. Okay. Now vi will be equal to va plus omega into rho A vector. Okay, where va is the velocity of that point here. Now arbitrary point as such, I can show you a figure here. You can see this is the corresponding arbitrary point here. Arbitrary point is any point, okay, it is not the mass center but any other point here. Okay, so I have attached secondary reference frame small xyz to the point A and it is embedded within the rigid body. So coming back, if I substitute here, now HA is also, angular momentum is also a vector here, as you know. I can, we had already discussed this, angular momentum is also a vector. Okay, so I can represent the vector sign everywhere here. So HA is equal to sigma rho A vector cross mi into VA vector plus omega vector cross rho A vector. Okay. Now if you expand this corresponding equation, you will get sigma into rho A vector cross mi into VA vector plus sigma rho A vector cross mi into omega vector cross rho A vector. Also vector. Okay. If I express this in terms of the integration rather than the summation, okay, so I get HA equals integral rho A dm cross VA vector plus, now as such I had changed the corresponding mi into dm here and I had shifted its position to this part. Why? Because as such VA is a constant and hence it is not affected by this integration here. Okay, that is why I have changed it into this corresponding format. Now plus integral rho A cross omega vector cross rho A vector into dm. Okay, this is the corresponding equation for any arbitrary point. Now next I would like to discuss is regarding the transfer principle which we had derived earlier for an angular momentum. Okay, so that based on the transfer principle, I told you the angular momentum can be transferred from the mass center to any other arbitrary point. We had derived this earlier when we discussed system of particles. So the same equation can be used here also. So as such, I can say the HA vector is equal to rho G with respect to A. Now rho G with respect to A is the corresponding position vector of the mass center with respect to the arbitrary point A cross m into V bar. Here it is given as VG or V bar, both are same thing, plus HG okay, where m is the total mass of the rigid body. Total mass of the body. This is a vector and this is a vector. So this equation also you will have to remember it out. The transfer principle. Okay. So I can transfer the angular momentum from the mass center to any other arbitrary point here. Now the next topic we shall discuss today is regarding the inertial properties. We had derived the corresponding equation for the angular momentum with respect to the mass center. It was a long equation. I'll show it to you once again. See this equation here. Okay. Now this corresponding equation can be simplified. If you express this equation in terms of the inertial properties of the rigid body. Okay, the inertial properties of the rigid body. Now you must have already studied regarding the inertial properties. Inertial property as such is the mass moment of inertia. Okay, the mass moment of inertia, which we call it as I. We must have discussed both area moment of inertia and mass moment of inertia in statics. The same thing. I'll just revise the concepts here for those who have not looked into that part. I'll just revise that topic here once again. So as such, the mass moment of inertia for a rigid body about any axis is given as say the corresponding axis is A, is given as integral r square dm integrated over the entire volume. Okay, integrated over the entire volume. Let me show you a figure here. Okay, this is the corresponding AA axis. Okay, and I have a corresponding differential mass dm at a distance r. So the mass moment of inertia of this entire rigid body with respect to this axis, IA is given as integral r square dm. Mass moment of inertia is a scalar quantity. Okay, it is a scalar quantity here. Okay, now you must have also discussed regarding the radius of gyration of the rigid body, the radius of gyration of the rigid body with respect to an axis. So the radius of gyration Ka is given as root of Ia by m, root of Ia by m. And you must have also studied regarding the parallel axis theorem. Okay, the parallel axis theorem. Okay, if you have the moment of inertia with respect to an axis AA, and if you have the corresponding axis that passes through the mass center of the rigid body G here, sometimes we call this as central axis. Now in that case, by applying the parallel axis theorem, I can say Ia is equal to Ig plus m into d square, where d is the distance between the two axes. This is valid only in case both the axes are parallel. Okay, when both the axes are parallel. So these things you must have already discussed in last semester. Okay, the parallel axis theorem. Okay. Now, instead of any axis I, if I want to find the mass moment of inertia with respect to the three coordinate axes, I have, say, this is the rigid body here. Okay, the distance from the corresponding axis are given as x, y and z here. Okay, now if we have a small differential mass dm here, the corresponding mass moment of inertia with respect to the x axis ixx, which is usually denoted by ixs, is equal to integral rx square into dm. Okay, means the corresponding distance from the x-axis. Okay, so if this is the mass here dm, its distance from x-axis, it is rx. Okay, it is rx here. Okay, now this rx can be written in terms of y and z here. So this will be equal to integral y square plus z square into dm. Similarly, Iyy, okay, is integral ry square into dm. Here, this is the corresponding value of ry. Ry I can represent in terms of x and in terms of z and x here. So this will be equal to integral z square plus x square into dm. Similarly, Izz is equal to integral rz square into dm. So rz square here can be expressed in terms of x and y here. So this will be equal to integral x square plus y square into dm. Okay, so these are the mass moments of inertia with respect to the three coordinate directions x, y and z. Now for problems that is related to the rotation of a three-dimensional rigid body, the angular momentum equation which we had derived earlier also consists of certain other terms. besides this y square plus z square into dm, z square plus x square into dm, and x square plus y square into dm. So to take that part into account, we have defined something called the product of inertia. The product of inertia. The product of inertia. The product of inertia, it is given as Ixy, or we can also call it as Iyx, both the same thing. That will be equal to integral xy into dm. Similarly, Iyz, or I can say Izy, is equal to integral yz into dm, and Izx is equal to Ixz is equal to integral z into x into dm, all with respect to the entire volume of the rigid body. Okay, so these are the inertial properties, these three plus these three. Okay, these are referred to as the inertial properties of a rigid body. Now this corresponding 6 terms is sometimes expressed in terms of a matrix, okay, which is referred to as the inertial tensor. Okay, inertial tensor at a point. Okay, so the I matrix, I is usually written as Ixx, or simply Ix, I'm write it as Ix only, then minus Ixy minus Ixz, then minus Iyx, Iyy minus Iyz minus Izx, I minus Izy, and finally Izz. Okay, so if you see that this corresponding matrix is called as the inertial tensor. The inertial tensor. Now the diagonal elements here are positive, while the off diagonal elements here are negative, and you can see that these two terms here are equal. So as such, this matrix is a symmetric matrix. So why that minus sign has been included? It is depending upon certain conventions in the tensor algebra, which is a different topic, so I shall not go into that aspect. Just need to remember the corresponding matrix I here. Sometimes what happens is that I can choose the XYZ axis in a particular orientation such that the products of the inertia becomes 0. Okay, I can choose the XYZ axis in such a way that the products of inertia becomes 0. That corresponding XYZ axis is called the principal axis. Principal axis. And the moments of inertia in the corresponding principal axis are called principal moments of inertia. Principal moments of inertia. Okay. The products of inertia equal to 0 indicates that Ixy, Iyz, and Ixz is equal to 0. That is what it means when I say products of inertia is equal to 0. So in that case, the corresponding matrix Ixx 0 0 0 Iyy 0 0 0 I z z. Okay, so to distinguish between the principal moments of inertia, when the axis is principal axis, Ixx will be referred to as I1, Iyy will be referred to as I2, and Izz will be referred to as I3. So as such, I can write it as I1 0 0 0, I2 0 0 0, I3. This is how you write the corresponding moments of inertia in case the axis is the principal axis. Now, the reason why I had discussed the principal moments of inertia is that you have seen the equation of the angular momentum of the rigid body with respect to the center of mass or with respect to a fixed point. That is given here. So as such, I had just copied it from the above. So you see those terms which we had discussed will come here. So you see this corresponding term is Ixx. This corresponding term is Ixy. This corresponding term, it is Ixz. And similarly all other terms as such come here. This is Iyx. This is Iyy. This term, it is Iyz. This is Izx. This is Izy, and this is Izz. So as such, HO or HG as such, HO or HG both will have the same corresponding format, can be given in terms of the inertial properties as Ixx into omega x minus Ixy into omega y minus Ixz into omega z into I cap plus minus Iyx into omega x minus plus Iyy into omega y minus Iyz into omega z into j cap plus minus Izx into omega x minus Izy into omega y plus Izz into omega z into k cap. Okay, or I can express this in terms of the components of H. So this corresponding will be Hx, this corresponding along with respect to j cap will be Hy, and this corresponding will be Hz. So as such I can write Ho vector is equal to Hx into I cap plus Hy into j cap plus Hz into k cap. So I express the corresponding angular momentum in terms of the scalar components Hx, Hy and Hz. Okay. Next, what we look into is certain special cases of the angular momentum. Okay. You see, in the above equation, in case the corresponding rigid body is restricted to move in a single plane, and that too the xy plane. Okay, say I call it as plane motion. Okay, the plane motion, this is a special case. So in case of plane motion in xy plane, in that case omega y and omega x will be equal to 0. Okay, omega y and omega x will be equal to 0. I will represent omega z as simply omega. Okay, so the equation which we had derived earlier, that is this corresponding equation here, will be reduced. Okay, so as such I will have hx as minus omega into ix z, hy is equal to minus omega into iyz, and hz is equal to omega into izz. Omega as such is omega z. Okay, so simply write omega z as omega here. So this corresponding equation gets reduced to this format. In case of a plane motion, the equation h vector is equal to minus omega into ixz into I cap minus omega into iyz into j cap plus omega into izz into k cap. Okay, here I am representing only the scalar values of omega. Okay, this is one case. Now in case the reference frame small xyz coincides with the principal axis, in case the corresponding xyz small xyz reference coincides with the principal axis of the body, then we can say that the products of inertia, that is ixy, iyz and ixz, all will be equal to 0. So as such the equation hx will become simply ixx into omega x, hy will become iyy into omega y, and hz will become izz into omega z. So as such the h vector will be equal to ix x into omega x I cap plus iyy into omega y into j cap plus izz omega z into k cap. The equation gets reduced to this format. Okay. Okay, so remember these two cases. One in case of the xyz coincides, the small xyz coincides with the principal axis. The other case in case of a plane motion. So now let's move on to the next topic, the moment of momentum equations. The moment of momentum equations. I told you there is a relation between the corresponding moment m and the angular momentum. M is equal to h dot. Okay, so how can we include that aspect here? Now suppose the corresponding small xyz frame is not embedded within the rigid body. Okay, so let omega be the angular velocity of small xyz relative to capital XYZ, and omega bar is the angular velocity rigid body relative to capital XYZ. So in the earlier case we had discussed omega is equal to omega bar. Okay, but now this is not the case. Now this is not the case. Now we had studied regarding the derivative of a vector. The derivative of a vector as seen from different reference frame. You have studied that if for a vector as such, the derivative of a vector dA by dt with respect to the capital XYZ is equal to dA by dt with respect to small xyz plus omega cross A, where omega is actually the angular velocity of the secondary reference frame with respect to capital XYZ. Okay, this equation we have studied. So same thing as such can also be applied here. the same thing can as such can also be applied here. I can say dH by dt, the derivative of the angular momentum with respect to capital XYZ is equal to dH by dt, the derivative of the angular momentum with respect to small xyz plus omega vector cross h vector. Okay, this corresponding equation we can apply. Okay, now the derivative of the angular momentum vector with respect to capital XYZ is the moment of forces with respect to that point. Okay, so as such I can write this as m vector is equal to dH by dt with respect to small xyz plus omega vector cross h vector. So this equation we had seen. Okay, now I know that h vector is equal to ixx into omega x minus ixy into omega y minus ixz into omega z, this into I cap plus minus iyx into omega x plus iyy into omega y minus iyz into omega z into j cap plus minus izx into omega x minus izzy into omega y plus izz into omega z into k cap. Okay. So if I take the derivative of this, if I take the derivative dH by dt, then I'll have to take the derivative of each of these terms. So m vector is equal to dH by dt vector. If I take the derivative of each of these terms, it will be a very lengthy equation. So I am not writing that equation as such here. I'll just write the final answer here. Okay. So as such, if I take the derivative and I express it in terms of the scalar components, and I express in terms of the scalar components mx, my and mz, okay, what I would get is that mx is equal to omega x dot ixx plus omega y omega z into izz minus iyy plus ixy into omega z into omega x minus omega y dot minus I into xz omega z dot plus omega y omega x minus I yz into omega y square minus omega z square. Similarly, my I would get omega y dot into iyy plus omega z into omega x ixx minus izz plus iyz into omega x into omega y minus omega z dot minus I yx into omega x dot minus plus omega z into omega y minus I into zx omega z square minus omega x square, and mz is equal to omega z dot into I z z plus omega x into omega y into I y minus I x x plus I zx into omega y into omega z minus omega x dot minus I zy into omega y dot plus omega x into omega y minus I xy into omega x dot omega x square minus omega y square. These three are the corresponding equations, mx, my, mz. There is no need of by hearting these equations as such. I just wrote it down to make you understand what you will get when you take the derivative of h. Okay. Now, as such, we may not require this equation because most of our problems which we deal in mechanics, in rigid body mechanics, are planar problems. Okay, so we may only require the reduced format of these equations, and in most cases what happens is that the corresponding xyz, the secondary reference frame xyz, is taken along the principal axis. So as such this gets reduced. So here I consider two cases. Okay, the first case is regarding planar motion. So if you have the corresponding rigid body that is undergoing motion only within a single plane, okay, the entire and all the different points in the rigid body are simply moving in along a single plane. Okay, the planar motion in case of thin slab like bodies, in that case, and that too within the xy plane. Okay, and that too within the xy plane. In that case, you have omega y and omega x as well as omega y dot and omega x dot is equal to 0. Okay, and as such I represent omega z as simply omega. Then the equation gets reduced. In that case, mx will be equal to minus xz into omega dot plus iyz into omega square, and my will be equal to minus iyz into omega dot plus ixz into omega square, and mz will be equal to izz into omega dot. Okay, so these equations are the reduced format of the above equation in case of a plane motion when omega y, omega x, omega y dot and omega x dot are all equal to 0. Maybe the last equation as such you must have studied earlier in the format of t equals I alpha, or you must have studied as t equals I into theta double dot. Okay, maybe you must have studied this equation in physics. Okay, so the same thing is what in a different way. Okay. Now the second aspect is in case of the xyz frame is oriented within the principal axis. Okay, the xyz reference is aligned along the principal axis. In that case, then the products of inertia, that is ixy, iyx, iyz and izx etc. will become equal to 0. Hence the equations get reduced to the format mx equals ixx into omega x dot plus omega y into omega z into izz minus iyy, and my is equal to iyy into omega y dot plus omega z into omega x Ixx minus Izz, and mz is equal to Izz into omega z dot plus omega x into omega y into Iyy minus Ixx. Okay, these corresponding equations are called as Euler's equations. Euler's equations is a very powerful tool when we want to study rigid body dynamics. Okay, it's a very powerful tool. Okay, so as such, we will wind up the lecture here. Remember one thing very clearly. You see, I had discussed both the planar rigid body motion and three-dimensional rigid body motion in one single lecture. In most of the textbooks, including Shames, okay, these are discussed as separate topics. Okay, but to have a better idea, to have a more general outlook, I had discussed it both together. In the next class, most probably, we will try to solve some problems related to rigid body dynamics. Just take an effort to memorize some of the equations we had studied in this class so that it can be employed effectively in the next lecture. Thank you all.